computations for large generative models such as Llama and OPT are performed with both weights and activations, being cast to 4 bits in a way that leads to practical speedups while at the same time maintaining good accuracy. We achieve this via a hybrid quantization strategy called QUIC, which compresses most of the weights and activations to 4-bit while keeping some outlier weights and activations in higher precision. Crucially, our scheme is designed with computational efficiency in mind. We provide GPU kernels with highly efficient layer-wise runtimes, which leads to practical end-to-end throughput improvements of up to 3.1 times relative to FP16 execution. Code and models are added at their GitHub.
Wait, can we go back for a sec? Let's handle. So they showed that the majority of inference computations, for large generative model can be performed with both weights and activations being cast down on 4 bits in a way that leads to practical speedups. The implications of this are absolutely profound because you could basically eliminate like 80% of the fat of the model, and it'll still be as intelligent as it was before. They achieved a hybrid quantization strategy called QUIC, which compresses most of the weights and activations to 4 bits, while keeping some outlier weights and activations in higher precision. So I don't know what they're doing for the compression to 4-bit, but while keeping some outlier weights. So basically what they mean here, they're going to scan through the whole network and they're going to keep some weights that are like dramatical values, like on a scale from from 0 to 10, like 9, 8, 7, those would be like the outliers to give you an idea. So they're going to keep some of those and some of the weights and some activations. So they provide GPU kernels with efficient layer-wise runtimes, which lead to practical and end throughputs. Okay. Yeah, so basically this is like sorcery because they essentially, they find a way to literally cut 80% of the weight of a model, and it's still able to perform at somewhat good accuracy. So like this, like that means 80% less GPU flops usage. And as we approach 1 bit, one day we're going to approach 1 bit or 2 bits, and we'll be able to like use LLMs with basically 0 computational consumption. So this paper, that lowering the computational energy consumption of LLMs is the main purpose of this paper. Do you have any ideas to add on to that, Zach or Dimitri?
No, that makes sense. Introduction. Large language models from generative pre-trained transformers family have gained massive popularity. One key contributor to their adoption by enthusiasts has been the ability to compress them using advanced quantization techniques, enabling local storage and effective generation inference for these models, even on personal computers. Yet the vast majority of work on quantization can be categorized in 2 cases. Weight-only quantization methods that help reduce the massive memory transfer cost of LLM execution, but do not reduce computation, and thus cannot provide significant speed for computational bound settings, such as prompt processing or large batch inference. Weight activation quantization methods, which can provide computational improvements, but either focus exclusively on 8-bit weights and activations, or execute with large amounts of accuracy loss relative to their uncompressed counterparts. Contribution. In this paper, we take a step towards bridging the precision gap between accurate weight only, typically 4-bit, and weight and activation methods, typically 8-bit. We present preliminary results showing that a large fraction of computation in modern LLMs, such as OPT and Llama 2, are performed accurately using 4-bit activation of weights. In figure 1 is an outlier-aware quantization with quick on the left, and the weight columns are extracted based on the outlier columns in the input. We commute the outlier columns towards the end of the matrix before applying the GPTQ quantization to accumulate quantization errors in FP16 columns. On the right, it achieves up to 2.4 times speed up with minor accuracy degrading on Llama 2 models. On the accuracy side, we show significant improved results relative to prior work by introducing hybrid selective quantization procedure, by which matrices are split into base weights and activations, which are processed exclusively at 4-bit precision and outlier. Weights and activations, which are processed at higher precision. Using this approach, as well as additional key insights on layer sensitivity, we can run the vast majority of computation in highly accurate models such as Llama 2 and 4, while dropping less than 0.5 complexity across both sizes. Importantly, our hybrid scheme termed quick is designed in a way that encourages minimal runtime overhead in a practical implementation. We demonstrate this by implementing efficient kernels, which show high per liter up to 2.4 times end-to-end throughput improvements relative to P16 baseline. Along the way, we also perform a study of efficiency, different low precision formats from current GPU architectures. Accurate quantization via quick. We focus on the task of accelerating linear layers with large language models, LLMs, by employing 4-bit quantization for both weight matrix W and input matrix X, following the PyTorch definition in 15. A linear layer carries out the linear transformation along with a bias vector denoted as B, taking the form of XWT plus B. We now describe the background and details of the technique. Weight and quantization. While there are several methods of accurate weight quantization, it is known that the activation matrices are hard to quantize. This is mainly because of the presence of the outlier features in such matrices. Corresponding columns have up to 100 times larger magnitudes. LLM.18 identifies and extracts the outlier columns of X during the forward pass and quantizes the rest of the elements with 8-bit. However, this method is not efficient at runtime due to the added computational cost of determining outliers on the fly. Recent work has shown that the outlier features are fixed for each layer across various datasets, which means we can extract the outlier indices offline using a small collaboration set. GPTQ weight quantization. GPTQ involves the quantization of a weight matrix W while retaining the activations in X in FP16. To achieve this goal, it aggregates the weight columns. For each column, it proceeds to quantize all of its methods simultaneously. Following this, GPTQ adjusts the remaining unquantized columns by using second-order information to compensate for the introduced quantization error in the current step. This process accumulates the quantization errors into less columns, making them more sensitive to quantization. Quick is an activation-aware GPTQ. During the linear transformation XWT, the outlier columns X will always be multiplied by certain columns in WT. We utilize this observation. It improves the quality of GPTQ quantization while quantizing part of the activations as well. To the sense that the outlier columns fixed across data sets, we begin by extracting the indices of the outlier columns by means of a collaboration step. Then we rearrange the weight columns and their corresponding rows and columns in the SU matrix to shift the outlier columns towards the end. Finally, we perform quantization on the weight columns up to the index of the outlier features. This circumvents quantization of these hard to quantize columns. It also helps to improve GPTQ quantization by aggregating the quantization errors to the columns we keep in FP16 and removing potential weight outliers from the 4-bit weight quantization scale. Weight clipping. Weight clipping improves quantization by trimming the input distribution before rounding. This could be done by either training the whole network to find the optimal clipping thresholds, 1, 6, and 18, or employing the heuristic methods, 9, 10, and 12. And we found that applying linear search over the clipping thresholds for weight quantization improves final complexity. Partial quantization. The described approach is efficient for the effective quantization of OPT models with a minimal impact on accuracy. However, highly accurate massive models such as Llama 2 7B present a unique challenge due to their feed-forward layers, which involve 3 linear transformers along with element-wise multiplication, as well as their use of GELU activations. More specifically, previous work has shown that the down project layer have a wide input distribution, making their quantization. We found that we can recover the accuracy by quantizing the down project layer using only 8 bits, without any additional changes to our method. We described the selection procedure and provide additional discussion in 2.3. GPU kernel support for Quick. We now provide a high-level description of the models in the Quick format and can be executed efficiently on GPU. At the execution level, the quantized matrix multiplication consists of 3 parts. 1. Quantization of activations. 2. Matrix multiplication of quantized inputs and weights. And 3. Quantization of the result. So here we have quantization and dequantization columns. So we get the 0 act and the scale act from the final 0 scale input. So for the elements that we get from the input and output elements we get from the output, we will loop over those and we'll get the outlier element from the element minus the 0 act divided by scale act minus the half range. And then we end our loop when we've turned the output in the 0 act scale. And then for dequantization, we'll get the to parameters input 0x, scale weight, and weights reduced. We're going to loop over the elements that we get from the input elements that we get from the output. And we're going to get x from the element times the x scale times the weight. And we'll get the shift from the 0 act plus the half range times the scale times the weights reduced. And then we get the out element from x plus the shift. As long as the activation quantization is asymmetric, we find 0 and scale out of a vector and then perform element-wise quantization, shifting the values to fit into int4 or int8 ranges. By 8 for int4, by 128 for int8, and half range in algorithm 1. The second operation leverages Cutlass support of int4 and 8 types and takes two quantized matrices and outputs the matrix multiplication result in the int32 format. The quantization of the matrix multiplication result involves the descaling of the input using scaling factors of the weight and activation quantizations. Due to the asymmetric nature of the activation quantization, we also need to perform shifting of the result using pre-computed row-wise aggregation of weight and zero factors of activations. In this case study for Llama 7b, in this section we provide a detailed description of how to use Quick to accelerate the Llama 7b model within the NLP module of the Llama 7b module. 3 linear layers are present, referred to as up proj, gate proj, and down proj. Up proj and gate proj share an input and apply their respective linear transformations to it. Subsequently, the output of the gate proj is subjected to a SILU activation function. Lastly, the input for the down proj layer is constructed by taking the downward product of the outputs from the up projection and the gate projection. Is the variance of the maximum of the inputs in different layers of Llama 7b on the left, and the down projection layers of significantly larger variance, resulting in poor 4-bit quantization on the right. So the layers have smaller outliers, which should be considered as zero outliers. Figure 2 shows the variance of the inputs across various layers of the Llama 7b model. The down projection layers have a large input variance due to the hammered product of the previous 2 layers, which result in poor 4-bit quantization. To address the issue, we employ 8-bit quantization for both weights and activations within down projection layers of Llama 2. Yet it's important to note that not every layer exhibits significant input outliers, and there is the possibility of having zero outliers in a specific layer. To achieve this, we define the threshold value t and keep the outlier features only if the maximum of the input magnitudes is larger than t. When applying this idea to Llama 7b model, we can keep up to 30 linear layers in zero outlier mode without a major trajectory jump. Here's the performance results, overhead breakdown of Llama 2 7b on a machine with 8 RTX 3090 GPUs. Speedup versus up to 16, and versus the ideal implementation without overheads for 4-bit and 8-bit quick kernels. And on the right is a performance breakdown of the quick 4B with 256 outliers in terms of backbone time versus quantization/dequantization overheads at different Llama 2 matrix sizes. The accuracy of the resulting Llama 770B model is presented in Figure 1 on the right. Full details of the impact of outlier selection and selective quantization are given in Table 1 on the right. In Table 2, in the next section, to illustrate the performance implications of the outlier choices in Figure 3, we provide end-to-end speedups for variants of plug-in-face integration. We use directly 8-bit and 4-bit kernels without preserving accuracy. Ideally 8 and 4-bit relative to our accuracy preserving quick implementations in both settings. Since we do not select outliers in the 8-bit case, quick 8 is similar to a re-implementation of the smooth font in our setup. Experiments are performed on a server with 8 3090s. We observed that the 8-bit implementation provides close to ideal speedups, reducing the number of GPUs from 7 to 5. However, it is outperformed by around 25% by the quick 4B, which reduces them required GPUs to 3 using less than 72 gigabytes of GPU memory. This performance impact of per-layer outlier selection and selective port function is shown in comparison with the ideal 4-bit. Quick 4 is within 20% of the ideal 4-bit performance. However, it is not known how such a model might recover accuracy. The justifications for this performance impact is provided in Figure 3 on the right, where we break down the pre-operation overheads by standard matrix sizes in this model. Specifically, we observed that the overheads of quantization/dequantization operations can take up a large fraction of the overall operation time, especially for smaller matrices. This provides an illustration of the trade-offs between performance and accuracy for a specific model. We provide a broader experimental validation in the next section. Experimental validation. General setup. We evaluate our methods on OPT and Llama 2 while using Hugging Face implementations of model definitions and datasets using smooth quant. We extract outlier indices using 512 random sequences from the PILE dataset. And for GPT weight quantization, we randomly select 124 samples with the sequence length of 2048 for the C4 dataset, and we apply the symmetric quantization to the weights and the asymmetric quantization to the activations. Flipping thresholds for the weight quantization grid are found via a simple linear search over a squared error. Our scheme quantized a 7B model with in less than 2 hours using a NVIDIA A100 GPU. Here in Table 1 is an accuracy for the results for the 4-bit models on the left, the perplexity of the 4-bit OPT models on WikiDex2 dataset, and the smooth quant RPTQ and OmniQuant results are taken from Reference 18 and the RPTQ denotes their improved efforts to the right. Quick abulation studies result on Orbit, Llama 2 family, and Falcon 180B, also Wikitext 2 perplexity. Accuracy comparison of OPT. First, we compare the accuracy of quick against the prior full-bit activation quantization methods. Smooth quant applied for the 4-bit RPTQ and OmniQuant. And on table 1 shows the result of the methods for the 4 large OPT models on the Wikitext task, as seen by the efficiently leveraging a small amount of full precision iron columns. Here 256, which is approximately 3% of OPT 6 the hidden size. Quick is able to significantly outperform prior 4-bit methods, dropping only 3.3 to 0.5 points in complexity relative to the full precision baseline. We emphasize that for fair comparison, Quick quantizes all of the backbone layers to 4-bit here. Llama 2 quantization. Next, we move to the state-of-the-art Llama 2 models where we abulate key parameters of the 8-bit down projection as well as the outlier count. Our main conclusion is that keeping the down projection layers in 8-bit is crucial to achieve high accuracy as it improves perplexity by more than 2 points across all models, and that increasing the number of outliers brings continuous small improvements. Adjusting the outlier count provides fine-grained control over the accuracy compression trade-off. Additional details are presented in Appendix A. On the 8-bit quantization, we evaluate the performance of Quick on an 8-bit ABB model and quantize all of the layers using 56 outliers. Following our intuition from Llama 2 models, we quantize FCT2 using 8-bit and keeping 124 outliers layer. The results are shown in Table 1. Show a similar pattern in Llama 2 where we keep the FC2 layers in 8-bit. It is crucial for preserving the accuracy. Zero outlier settings. Next, we study the result of keeping some of the layers with 12 outliers in the zero outlier settings. Table 2 shows how the accuracy of Llama 2 and Falcon models change when we use different threshold values. Extracted using a linear search for the outliers. The results show that there isn't any universal threshold for all the models that optimize both accuracy and performance across the models. For example, Falcon ADB can recover the accuracy even if 24% of the linear layers, 15 out of 48, contain zero outliers. However, this is not the case for smaller names. Llama 70B can recover the accuracy of with up to 5% of the linear layers, 30 out of 560 without having zero quick outliers. Additional evaluations. In the appendix, we perform additional evaluations on the quick models and various other tasks, including PTB and C4 data sets. Overall, they show similar patterns to the Wikitext results above. Figure 5 is a layer-wise speed up on single RTX 3090 for different layer sizes and compression types. Quick 4B with 56 outliers and quick 8B without outliers. Ideal and layer size and layer-wise speedups. The results in Figure 4 depict the ideal computational power for layer-wise matrix multiplications at different precision levels without taking into account any quantization/dequantization correct. The results motivate all approaches. They show that significant speedups could be achieved via lower precision, especially for these operations. Motivated by this observation, we turn our attention to realizable speedups when executing algorithm 1, which includes the compression and decompression operations required for obtaining higher practical performance. In Figure 5, we compare layer-wise performance of optimized linear layers relative to FP16. For a full implementation of our algorithms, the matrix sizes correspond to the layers in the llama models. We observed that the quick 4B can achieve around a 4 times speedup on large models and more than 2 times on smaller ones. Thus, the raw, low precision speedups can partially add the overheads of quick end-to-end speedups. Finally, we also demonstrate the end-to-end speedup benefits of the quick models. For this purpose, we integrate quick into the widely used Hugging Face PyTorch.
People say that you have to have a lot of passion for what you're doing, and it's totally true.
Widely used Hugging Face PyTorch implementations of OPT and 1 or 2 for replacing the linear layers with 4-bit and 8-bit. Quick re-implementations for the llama model, and we use the standard flash attention implementation for llama models. In Figure 6, we compared throughput improvements of the pre-fill phases for the single batches, 248 tokens. The quantized models with the corresponding FP16 version. The bar plot shows the throughput improvements of the quick 4B compared to FP16. Annotations to the baseline represent the actual values of the baseline throughput in our experiments. For its OPT6B uses FP16 linear layers accompanied by 8 GPUs, achieved 439 tokens, whereas the same model Inference with the quick 4B layers tried only 2 GPUs and result in 153 tokens. In addition to the close to 4 times memory reduction, which reduces the number of required GPUs for inference. Quick also achieves up to 3.1 times higher throughput relative to FP16, with the biggest improvements obtained on the largest models, where the relative impacts overheads is lowest. Here in Figure 6 is an end-to-end inference speedup for quick 4B with 56 outliers relative to the FP16 baseline of the NVIDIA RTX 3090 GPUs. Notes over the bars state the minimal number of GPUs required to run the inference. We emphasize that the speedups in this end-to-end experiment are exclusive to the quick acceleration linear layers. As all other overheads are precisely the same. We observe the overheads from Potential softwares for layer guard operations become significant once a large fraction of the computation occurs in 4-bit, which could be optimized further in our implementation. Conclusion and further work. We have presented a new hybrid quantization scheme called QUIC, which allows us to execute vast majority of inference computations using weights and activations quantized to 4 bits. QUIC minimizes the accuracy loss by keeping the hard to quantize outlier layers in higher precision. Importantly, QUIC can be efficiently supported on GPU hardware, presenting significant speed-up potential, especially for inferencing on large models. Any thoughts? We'll get to the base code for this.
This looks really fun. Like, can you go back to the matrix diagram? Go down. Yeah, go up, go up. Yeah, this. Let's analyze this a little bit deeper. Okay, so number one, we have extract the outlier features from the input. You see the outliers, how big or how like they're just like radical numbers. So you see here, like the majority of the numbers are 0.12, 0.8, 0.91, 0.9, 0.48 on the first column. Then you have negative 91, 29, 65. That whole column is just a bunch of outliers. Then we go to the next column. Then we have 0.65, 0.51, 0.53, negative 18, 0.64, 71, 0.71. Then we have 121, negative 99, 85, negative 76, 81, 72. So the outliers are just like radical numbers on either side. They can be big, small. Then the next step is to identify the corresponding weight columns. So okay, so the first one is the input, the X. Then we have the weights. Then we identify corresponding weight columns. So then we're Dimitri, what do you think about this? So we identify the corresponding weight columns. We're looking for the weight columns of. Wait, can you just go down, Zach, a little bit? Yeah, so outlier aware quantization. Left, the weight columns are extracted based on the outlier columns in the input. So for every column, they're taking the outliers. Then they permute the outlier columns towards the end of the matrix before applying GPTQ quantization to accumulate the quantization errors in the floating point 16 columns. So the second image, they're identifying the corresponding weight columns where the features would go to, if I'm not mistaken. Or no, they're just looking for weight columns. Are they taking outliers again? No, they're not taking outliers again. So then the third step is to push them to the end during GPTQ quantization. Okay, so they're identifying the weight columns, then so they permute the outlier columns towards the end of the matrix. That's what they're doing in the second image. They're permuting the outlier columns towards the end of the matrix. Then 3 is they're pushing the weight columns to the end of the matrix. So the first 3 rows, as you see, are integer or 4-bit, and then the last 2 are just 16-bit. So that's basically how this works. What do you think, Zach?
Most of it goes over my head.
What happened?
Well, I don't understand it, really.
What don't you understand?
So,
So they're just taking a bunch of matrices, then they're finding the outlier values that are extreme. They can be both ways, extremely positive or extremely negative. Then they're taking them, then they're subtracting them and adding them and multiplying them with each other.
okay.
So they're just trying to find a way, because they have 16 bits now, or even 32, right? So they're trying to compress the model without it losing information. That's why they're extracting the outlier features.
Oh, yeah, that makes sense.
So they're trying to compress without causing a significant decrease in reasoning. That's the whole point of 4-bit quantization. So when you use a 4-bit model, what's happening is if we were to use this model, for example, the first three, or like the first couple of rows in the weights and the neurons of the model, are going to be 4-bit. But at the end of the matrices, you see there, the last two are going to be 16-bit. That's why it's able to still be very lightweight, but also be able to reason somewhat intelligently.
Yeah. Okay, and that makes some more sense. Thanks.
Yeah, so again, the whole purpose of this paper is trying to compress models, make them easy to run on any hardware, while also maintaining their ability to reason. So that's what they're trying to do by extracting the outlier features. Then in the second image, permuting the outlier columns towards the end of the matrices, and at 3, you see they push the 16-bit to the end.
Okay.
Is that the code?
Well, it's where the code should be, but
it isn't.
Released it yet.
I'm going to implement this. Yeah, this is pretty crazy stuff, because like I said, the whole purpose of quantization is to radically eliminate the need for high GPU consumption.
Yeah. Evelyn, do you think you could help me to do this